Welcome to Unit 5. As you may already know, integrals is the last of the four really big concepts in calculus. And integrals, when it comes to the real world, are a tool that help us understand how the rate of something changing affects that total amount of whatever the thing is that's changing. Intuitively, in some ways, you can think of them as the opposites of derivatives, although the techniques we will learn may not seem totally related right at first. Ultimately, in this unit, we're going to talk about the area under a curve, and then we're going to use some notation called a Riemann sum. Then we'll learn about something called a definite integral, then antiderivatives, and we'll end with something called the fundamental theorem of calculus, which is a huge theorem that culminates in a little trick that will help you answer integral questions. Let's start with area. By the end of this video, you should be able to use rectangles to approximate the area underneath a curve. That's what your homework quiz will be on Monday morning. Before we get into the details, let me just give you the main idea behind integrals. Basically, an integral, which is represented using this kind of elongated S notation, anytime we take the integral, we are representing the area under a curve of a particular function. Mathematically, you can kind of get the idea we're talking about functions, and this red space is the area. Well, why do we care about the area? If this curve is a derivative function, as in it's the derivative of a different function, then the area under the curve represents the accumulated total of the original function's output. In other words, whatever the original function was measuring, this area, the area under the derivative graph, tells us how much there was after a certain period of time. This should be enough to convince you that area is going to be a really important component to understanding integrals. So let's go deeper into this idea of calculating area. Look at these two graphs. Which of these two areas, the blue one or the green one, do you think would be easier to calculate? Exactly. I expect most of you probably said the green area. And it's a very simple reason, is just that this is a triangle, and we can use the area formula for a triangle. So that's why this is easier. If we had to summarize why this blue one is actually challenging, we would say, well, because when we have a curved irregular shape, we don't have a formula for measuring the area of it. We can kind of eyeball it. It looks like it's a pretty similar area to this triangle, but eyeballing isn't really good enough. So this was the challenge that Newton and Leibniz were facing as they were in the process of inventing or discovering calculus. And they came up with a pretty simple idea as a solution. Maybe it's something that occurred to you. If we take this blue area, and if we're willing to just come up with an estimate, which isn't a perfect value, but it's an estimate, we can take this blue area and kind of divide it into shapes that are easier to calculate. Rectangles, for example, are pretty easy. And if you look at these rectangles, the area of all these rectangles added together is going to be pretty close to the area of the blue curve. Obviously, it's not perfect. Here's some area right here in the blue curve that's not represented inside my green rectangles. And here's a place where the green rectangle actually steps outside of the area that I really want. But it's an approximate. This should be a pretty simple idea. In fact, let's go ahead and just try this, see what it feels like. We're going to estimate the area under the curve of this parabola. Notice that it's a downward-facing parabola. Okay, so we've got the idea here. How are we going to start? Sure, we probably need a graph first. So grab your graphing calculator or move over to Desmos, which is what I'll do, and go ahead and graph this parabola. What you should see is that you end up with a parabola that looks like this. And when they say estimate the area under the curve, what they really mean is this part up here, the part that I've just shaded in green. So we want to come up with an estimate of this area. Remind me again, how are we going to try estimating it? Exactly, we're going to draw some rectangles. And you get to choose, actually, how many rectangles you want to draw. For the sake of consistency, let's all do 4 rectangles. So in your notes, go ahead and sketch this parabola. And on top of the parabola, sketch 4 rectangles that more or less follow the shape of the curve, kind of like we did here. Cool, so this is what my sketch looks like. Maybe yours is kind of similar. It could look a little different. What should be the same is your 4 rectangles should be kind of tall and skinny. They should start at 0, and they should end right here at 8, because 8's the place where this particular parabola hits the axis. And you could see that either from looking at your graph or from calculating the roots. So we want to estimate the area. Well, just a second ago, we said basically the idea is that the area of the green region is approximately the area of each of these 4 rectangles added together. So all I really need to do is figure out how to calculate each of these rectangles' area. How do you calculate the area of a rectangle? Exactly, it's just base times height. So basically, my total area is just going to be base times height plus base times height plus base times height plus base times height. Now, be a little careful. Actually, each of these bases are different. This first base times height represents the first rectangle right here. So we want this base distance and this height distance. The second B2H2 represents this second base times this second height. So each of these numbers are different and they're not like terms. I use the subscripts to say I'm talking about the first rectangle here, the second rectangle, etc., etc. And then the beautiful thing is actually looking at the way we've drawn our graph. Because we chose to do 4 evenly sized rectangles, the truth is all of these rectangles do have the same base distance. And we can figure out what that is by thinking about the total length here. Going from 0 to 8, that total length is going to be 8 units. And then if I want 4 rectangles, all we need to do is divide. You take the total length 8 and you divide by 4, and it's obvious that each of these rectangles has a base of 2. Which is great, because really that means the only thing I need to do to create this very simple estimate is to figure out what the height is for each of the 4 rectangles. There's a couple options for how you can do this. Of course, since you're looking at a graph, you could just eyeball it. And you could look at this and say, well, this first rectangle looks like it's about 4.5 high. But that should be pretty unsatisfying, because there's a pretty simple thing we could do to get an actual accurate estimate of how high this rectangle is. If you look at this rectangle, notice that the top of this rectangle, the height of it, is the same as the height of this point right here. And this point is a point on the parabola that has an x value of 1. So knowing what the x value is and knowing the function for the parabola allows me to calculate the y value. And the y value of this point is the same thing as the height of the rectangle, because this point represents the top of the rectangle and this point is on the parabola. So if I wanted to calculate the first height accurately, all I need to do is take that x value 1 and plug it into the function equation, which is that top one up there. You can do this in your head. 4 times 1 is 4, 1/2 times 1 squared is 1/2, and 4 minus 1/2 is 3.5. You can also, since we're about to do this a bunch of times, put the equation into y equals, looks something like this, and then go to your table. And, oops, that's the graph. When you go to your table, you can use the table function to calculate the heights exactly. And you want to calculate the height at 1, which is the midpoint of the first rectangle, and then at 3, which is the midpoint of the second rectangle, and then at 5, which is where the third rectangle has its height, and then at 7, which is where the last rectangle has its height. And these heights, which just come from plugging in those x values to the parabola's function, these heights, or y values, give us our heights of our rectangles. And when we add them all together, we get our estimate of 44 units squared, which is just an estimate, but not too bad. It's very little work. This idea of using rectangles to estimate area is called the rectangular approximation method. And this is the idea that Newton and Leibniz and a bunch of other guys came up with in order to figure out how to calculate the area of a strange shape. Basically, it has 6 steps. These are the 6 steps that we just did. We sketched a graph, we identified where the shaded region starts and ends, we chose how many boxes we wanted to use, and we calculated the width of each box using the entire length, so 8 minus 0, divided by the number of boxes, which was 4 for us. And then once we had the width of each box, we calculated its height, and we did that by plugging in the x value from the bottom of the rectangle into the parabola's function, f of xi. Ultimately, we added them all up. Pause for a second on this screen to make sure that you really thoroughly understand what each of these steps are. Right, so hopefully they all should be really easy, except maybe step 5, because step 5 takes a little bit of work, making sure that you have the right x values. Let's go into some more detail about that. There's actually 3 different ways that you can choose the height of your rectangles. These 3 graphs all represent the same parabola we were just working with, and they represent 3 different kinds of approximations. This one's called the left-hand approximation, this is called the midpoint approximation, and this is called the right-hand approximation. Look really carefully at each of these graphs and the way the rectangles are drawn. How are they similar? How are they different? Right, so hopefully what you noticed is that the rectangles all have the same width in all 3 graphs, but the difference is the height. In the left-hand approximation method, the height of each rectangle is the same as the left-hand edge where it hits the parabola. In the midpoint approximation method, the rectangle intersects the parabola at the midpoint of the top. In other words, the height of each rectangle comes from plugging the midpoint in to the parabola. The right-hand approximation method, the height of each rectangle depends on the right-hand edge. So here we would plug in the right-hand x value into the parabola and get that height out. Let's do an example to see how these differ from each other in practice. We're going to approximate the area under this function between 2 and 8. You should start with a graph. This is what the graph looks like. Again, the function itself is just this kind of curvy thing. And then we are interested in the area underneath the curve, starting at 2 and ending at 8. You should pause here, sketch this in your notes to get started. Don't shade it in quite yet, because we're going to do an estimation by drawing rectangles. Great, so you should have a sketch in your graph. Maybe it looks something like this. And we're going to estimate this area using 4 rectangles. And let's first use the left-hand approximation method to get the heights of those rectangles. The plan will be to add up 4 different separate areas. I think sketching is really helpful to start to conceptualize what these areas are. So mark on your graph where the shaded region starts and ends. And make sure to note down that we want 4 rectangles. If we're starting at 2 and ending at 8, how long is this distance right here? Exactly, 8 minus 2 is 6, so we have a total distance of 6 units on the base. If I want 4 rectangles, how wide should each of them be? Well, we would do 8 minus 2, which is 6, divided by 4, is actually going to be 1.5, and that's where we calculate the width. What that means is that each of these areas is going to start with 1.5, and then it's going to be multiplied times the height of that particular rectangle. So let's visualize the first rectangle. The first rectangle obviously starts at 2. If its width is 1.5, it ends right here at 3.5 in the middle, and we can draw that going up. Now, if we're using the left-hand rectangular approximation, the height of the first rectangle is going to be the same as the height at 2, because that's the left-hand end of this first interval. So my rectangle would look something like this. To figure out the actual height of that rectangle, I really just need to know the y value of this point. And I can calculate that by plugging the x value 2 into the function f, which is this function right there. Again, I prefer to do this using my calculator by putting the function into y equals and then going to the table, and I can just type in 2 for the x value. And I get a height of 2.482, which then becomes what I multiply for this first term. Similarly, the second rectangle is going to go from 3.5 all the way up to 5. It's going to get its height from the point when I plug in 3.5, and that value will plug in here. The next rectangle will get its height from the x value of 5, and that'll plug in here. And the last will get its height from the x value of 6.5. Again, I'm just adding 1.5 each time. And when I multiply and add them all up, I end up with an estimate of 22. You should try doing this using the right-hand side y value instead.